This is Mrs. Carreri's solution discussion for Progress Check Unit 2, Multiple Choice, Part B. Part A and B, by the way, they design them so that you could take A in a 45-minute class. Just keep that in mind. They expect you to be able to do the entire MCQ Part B in 45 minutes. At any rate, here we go. We have 3 blocks, M1, M2, M3. It's pulled to the left by a force. There's tension TA and there's tension TB. We know that the blocks M3 is greater than M2 is greater than M1, and friction is negligible based on the information they provided to me in that sentences. They have three free body diagrams drawn for you, labeled. Notice they use T's for tension instead of FT, which I don't like, but whatever. And they want me to know, how does the force, the string tensions TA compare? So which one's greater? Obviously, you know A is correct, but let's see how we got that answer. In other words, is force greater than TA? Is TA greater than TB? Is one of them equal to one another? I summed all the forces around 3. I started that over here. And I found that the tension of B is equal to mass 3 times acceleration. A is the same for all 3, okay? And acceleration is to the left. We will assume acceleration is positive and all the forces in that direction are positive and all the forces in the opposite direction are negative. Then I summed the forces around M2 and I got TA positive minus TB negative is equal to M2A. Solved for TA and plugged in what I found earlier for TB and found that TA is the magnitude of M2 plus M3 times acceleration A. Then I did the same for the first block, and I found the force F, because I got to be able to understand how F is. So again, here's the first equation, the first step. Force minus TA equals M1A. And then I took what I had just developed for TA, plugged that in, and came out with, moved everything around. Whoops, I don't like that one. And then plugged in the value of TA in there. You could do the whole system if you'd like. Anyway, here we go. Now I have an equation for TA, TB, and F. Now notice, TA equals the total mass of M2 plus M3A. TB just equals M3A. And force F equals all the 3 masses added together. So hopefully you see that force has to be greater than TA, which is greater than TB. Alrighty? Now, which of the following is correct ranking of the normal force? Fn1, Fn2. Well, they kind of helped you with that. They told you that M3 was greatest, and notice that's the longest. This is the second longest. That's the third longest. I hope that one's pretty straightforward. Now, the student is trying to determine the tensions in the string that's connecting the boxes. If the acceleration, this is number 3, if the acceleration of the system and the pulling force are known, so A and F are known, which of the following pairs of equation could be used to find tension? So I know A and I know F, and I'm just going to go look at the equations that I have up there and determine which one could be used to find TA and TB. So TB equals M3A. Hold on. Yep, there it is, first one. There's what I derived up there. And then if I go look at the second one, I need TA. TA is equal to M2A plus. Yeah, all they're doing is sum of the forces around the second block. TA minus TB equals M2A2. They haven't rearranged anything. Look at this. I'll tell you how you can figure out if it's right or wrong. This is a correct equation around number 3. That is not a correct equation around number 2. They left off TB. I got to take a pause. So I'm going to get ready to cough. Hold on. Okay, I was trying to help you understand how to see the wrong ones if you couldn't quickly determine that B is the correct one. Look at C. If I sum the forces around that have F in it, so look at where F is around block 1. So F is equal to, or I'm sorry, F minus TA is equal to M1A. F is not acting on the third block. Okay, F minus T, this is correct, but that first part is incorrect. So this is correct. That is true statement. Newton's second law apply to block 1. But this is not correct because we left off minus the tension force in B. So this is incorrect. So you could have also done it by a process of elimination. Number 4, students attach a force probe in the middle of a string. What does that look like? So here is a force probe. I've redrawn it. I can put a force probe in the string. I can actually put it in there and I can get a data point, okay? In the middle of string A to measure TA. And then they use a force probe right here to determine the force that is applied, the F. All right, so we have this F and we have this T. All right. Now listen to this. When the box of mass 3 is held, so some other student hangs over here by a student, he's holding on to this. And a second student comes over here and pulls on that force probe to the left. And that provides an applied force F. Okay, so think about it. I'm pulling to the left, the other student's pulling to the right, and everything remains at rest. Acceleration equals 0. The net force on each one of those things has to be equal to 0. This force here, force applied, should equal that force of tension, TA, which is pulling to the right on M1. So here's all the data: 10.6, 11, 10.4, 10, 10.2, 10, 10.8, 11, 10.6, 11. Yes, I realize that is not perfect, but data is not perfect. Those probes are not maybe calibrated exactly right, or the electrical signals aren't exactly, the digital outputs of them scales, or one's older than the other and it's not quite as sensitive. Who knows? A, the two quantities exactly agree numerically. No, they don't. The two quantities agree within some experimental uncertainty, but they do not exactly agree numerically. They are not exactly numerically, but as far as I'm concerned, they're experimentally the same. So that's why B is correct. The two quantities disagree by an amount that is larger than what you would expect. No. The two quantities cannot be compared because the two force probes have different levels of precision. I don't know. There's nothing in that statement that even came close to that. So moving on. Number 5, how does, a hockey player is used to hit the puck with a stick. I have a picture over here. They give me a whole bunch of information, which is not needed, by the way, to answer this question. They give me a distance, they give me a velocity, they tell me that the thing travels at a constant speed. But here's the question. How does the magnitude of the force exerted by the stick on the puck, now there's that is the force the puck puts on the stick, compare to the magnitude of the force exerted by the puck on the stick? Everybody might want to think that the stick gives a larger force on the puck than the puck does on the stick, but Newton's third law says they are equal in magnitude. Notice they said, how does the magnitude compare? So that is a third law pair question. No calculations are necessary. Okay, number 6. Which of the following statements best describes the force or forces exerted on the puck after it is hit by the stick and slides on the ice. So we got to go back up here. So what they tell you is that this is important statement up here. Where is it? Constant speed after it's hit. So acceleration is 0. So if you were to draw the forces on that, all I know is that they add up to 0. Force normal, force of gravity. Since there is no force applied after it takes off from the stick doesn't follow it, so there's no more force applied. That means force of friction can't be there. So the applied force from the stick is still exerted during this time. No, the stick doesn't run past it and keep up with it. Since the puck's acceleration is 0, there are no external forces acting on it. That is not true. We still have force of gravity acting on it, force normal from the ice. There is no frictional forces exerted on the puck. That is true. A normal force is not exerted on the puck. That's not true. No need for me to continue reading. There is no frictional force exerted on the puck. That is true. We have a gravitational force and a normal force are exerted on the puck. They're equal in magnitude and they're opposite directions, so they add up to 0. Number 7. There is a motorized cart, and you can tell that he's got his little trails, whatever you want to call that, and it's moving to the right. The motor is causing a force on that cart to be to the right. It's creating a force. That's an external force. It's actually caused by the friction between the table and the wheels, but okay. There's a cart. It's attached to a string that passes over a pulley. The other end of the string is attached to a hanging block, In the figure above, the cart is accelerating to the right. So we know that we're accelerating to the right. If I have a dot that represents that cart, I've got a force from the motor, and then I've got tension pulling to the left, and that force of the motor has to be greater than the force of tension. Which of the following best represents the forces acting on the cart at the instant shown? Oh, look at that. So A cannot be right because the applied force is smaller than the tension force, and we know it's accelerating to the right. So that doesn't work. B, again, it shows 2 problems. Applied is smaller than tension, and force of gravity is smaller than force normal. C, force normal and force of gravity cancel each other out, and the applied force is larger than the tension force, which is good because acceleration is to the right. So it's correct. D, the applied force is correctly drawn relative to tension. However, force normal is greater than force of gravity, and that's not correct because then I'd be accelerating upwards. So that explains why C is correct, A, B, and D are incorrect. So here we go. We have another problem on an incline. I got a block. We got block slides with a constant velocity, A equals 0, down a rough inclined plane. Rough implies friction that makes an angle of theta with the horizontal, otherwise known as the angle of incline. It experiences 3 forces, Fg, force normal, and frictional force. They show it, and this is how they always show it, correctly drawn with the angles. I don't like looking at it that way, and I will draw it as I have shown to the left. So I have to see it in the XY plane. It helps me visualize what's going on with my forces. Force normal's in my new Y, force of friction's in my new X. Which of the following gives the magnitude of the net force? That's really all I have to do is answer that question. I don't have to do anything else. Acceleration is 0, net force. If the net force is 0, acceleration is 0. If the acceleration is 0, the net force is 0. I don't know how else to explain it than that. I hope you understand that one. Number 9, in the setup in the figure, 2 blocks of equal mass are at rest, but are just about to slip. If we're just about to slip, we have a couple things we know. Static friction is at its maximum. Acceleration can be assumed to be 0. They also show a free body diagram for you, acting on the block that's on the table. hold on, as shown in the free body diagram for the block on top of the table, has to be the top, right? In this edit, the coefficient of static friction between the table and the block must be, well, don't guess. I want to guess, don't guess. I'm going to solve. I've solved it already to the right. I'm going to sum the forces. I'm going to sum the forces acting on the system, okay? The system, the two block system. Here's my system, right? There's only one force that's trying to accelerate me downward. It's mg. There's only one force that's trying to stop me from accelerating, and it is the maximum static friction. And by definition, the maximum static friction is mu s Fg. F normal. What is the force normal acting on the block sitting on the table? Well, that happens to be capital Mg. And because I'm just about to slip, the acceleration is 0. Okay. So I can rearrange that, and I'll have Mg equals mu s Mg. Whoops. No, I don't want that. Do that. Okay. I've rearranged that there, and then I've divided both sides by mg. Mg divided by mg is 1. Mu s has to be at least 1. Okay. Don't guess. And the reason why it came out to that way is because both blocks have a mass of m. All right. Okay. I like these kinds of problems, by the way, these blocks like this. All right. M1, M2, M3. I got T2, T1, force 0. 3 blocks with masses. M1, M2, M3 are attached by strings as shown in the figure above. The coefficient of friction between each of the blocks is mu. Okay, so all the blocks have the same coefficient. The tension in the left and the right strings are T1 and T2 respectively, or vice versa. The acceleration of the block is A. Which of the following expressions is equal to T2? Now, I started writing all the equations up above, and then I looked at the answers. Look at the answers. The answer has T1 in it. Every answer has T1. So go and find the free body diagram that has T1 and T2 in it and solve for T2. So it's the middle block. It's the middle block right here. T1 to the right, T2 to the left. Since I'm accelerating to the right, friction is to the left. I apply Newton's second law. T1 minus T2 minus the force of friction, which is mu k force normal. Force normal in this case is m2g, has to equal m2 times acceleration. Rearrange that equation for T2, which is what they asked me for, and I am now capable of using that approach to define an answer in terms of T1, M2, mu, and g. So use your answers sometimes to help you understand where to get started. Because there was a multitude of things. I could have used M3 and I would have been like, okay, M3 is in there. No, M3 is not in the answer. So, all right. Number 11 has nothing to do with that problem. So let's use that one. Number 11, I got a person going down, jumps out of an airplane, has a parachute. Okay. Sometime later, the parachute system and the drag forces are equal in magnitude. The weight of the skydiver parachute system. So the mass, the weight. Okay, what's the weight? That is Fg, which equals weight, okay, which equals the mass of the skydiver's parachute system, is now equal to the drag forces. Consider drag forces like a frictional force. We don't talk about air resistance in this situation, but hopefully you could see that a parachute causes a lot of air resistance. That's how we use parachutes. So now they are equal in magnitude. So the skydiver is now traveling at a constant speed if that resistive drag force is equal to the weight of the parachute skydiver system. Okay. All right. Number 12. In the following figures, each show vectors represent the forces acting on an object that is initially at rest. In which case will the object remain at rest? This is kind of like the first law. I need a net force of 0. All the forces have to add up to 0. So if I look at A, I can see that the force to the left and right cancel each other out, but I have more force upward than I do downward. Therefore, I'm going to accelerate upward. That is not the correct answer. B, same thing. Left force is smaller than the total right force. I'm going to accelerate to the right. I'm going to go to D. This is one people often pick. And if you were to take the forces that are in this direction that I just highlighted in green and break them up into their X and Y components, okay? There's a piece of the top one that's in the X direction, which is equal to the piece of the bottom one in the X direction, and I have to double that length. I've got two of them. So that is why there is a larger force to the right in the X direction than there is in the X direction to the left. Now, each of those angled forces have a little piece of Y, but both of them are identical, and then one's up, one's down, they cancel each other out. So I'm accelerating to the right in the X direction in that case. Now, C is the correct answer. So you have to visualize this. I have this little piece that's there. I have this red piece, which is the reflection of the one that's angled. And if I took those two pieces and add it together, it's pretty close to this visually. Same thing, I've got this piece, which goes all the way down to the center. And now I've got to add this piece, which is the reflection of that one in the Y direction. And I have to visually say, okay, it's approximately the same length as the one that's pointing downward. And therefore, the net force acting on that object is 0. Okay, this is a good one. I like this one. Number 13, I have a person that kicks a ball up in the air with a force F0. So here's the ball on the ground. They come along with a net force of F0, hence why it accelerates upwards at an angle, and the net force goes away, and now it's in free fall. And when an object is in free fall, you know that the acceleration in the X direction is 0, and the acceleration in the Y direction is downward due to the gravitational field that it's in created by the Earth. So its acceleration is downward by little g, the magnitude of little g. So what it wants to know is what is the net force on a ball and its acceleration at the highest point. So at the highest point, if you drew a free body diagram acting on the object at the highest point, the only force acting on it is Fg. So what is the acceleration? You could sum the forces in the y direction. It equals the mass times the acceleration. The only force is Fg, which equals ma. So mg equals ma. The acceleration of the object is g, downward. I left out my negatives, but I think you hopefully see that. Okay, I actually did not leave out my negatives here. Okay, I often consider down positive just to make my life easier. So what does it say? What is the net force acting on it? Well, the net force is the sum of all the forces. It's the force of gravity. And then what is the acceleration? G. Hence why B is correct. There is 0 acceleration in the X direction, net force of 0 in the X direction. This is the force that was used to kick the football or the ball, but that force did not follow it all the way up to the top. Okay. All right. Don't get tricked by that force applied following that object. There's quite a few people that do that. 2 astronauts of identical mass, that means they're identical, are connected by taut tables of negligible mass. The little cable is massless, as shown in the figure. They're initially at rest and with respect to a nearby space station. Astronaut Y pulls on the cable towards herself. So she puts a force on the cable, which then puts a force on astronaut X. Okay. Originally, I drew the center of mass approximately in the middle. That's the system of the astronaut X, astronaut Y. Okay. And if I wanted to, I could draw a dot that represents the center of mass of the astronaut Y, astronaut X system. Okay. Which of the following describes the direction of the velocity of the center of mass of the 2 astronauts after they pull? Okay, so if they're at rest originally, which is what they told me, that center of mass is originally at rest. So where's the external force coming from? There is no external forces. There's internal forces. They happen to be in opposite, they happen to be third law pairs, but there is no external force on the system. So acceleration of the system is 0. The velocity initial of the system is 0, and that means the velocity final of the system is 0. That center of mass, the velocity will not change. So the center of mass location, that dot, will not move. And that's why no external force was present on the system that was defined for us. This next one's a good one. I like this one. Another center of mass discussion. Number 15, I have 2 blocks, 3 kilograms, 2 kilograms on a Atwood machine. The 3 kilogram is upwards, higher located than the 2 kilogram. I'm going to let go of it. It's going to move. 3 kilograms going to go down, 2 kilograms going to go up. I have visually thought of the center of mass of the 2 block system to be closer to the 3 kilogram block initially. Okay. All right. Now, sometime later, after I let go of it, the 3 kilogram block is going to be on the ground, and the 2 kilogram block is going to be located a little bit higher. So just imagine that. And now the center of mass still stays closer to that 3 kilogram block. Okay, that red dot now represents where I think the center of mass, if I just visualize it, where it might be sometime later after I let go. So what is happening to the center of mass of the 2 block system? It started at rest and then it started to accelerate downward, okay? Because the net force on the system is in a downward direction, okay? What's the net force on the system? Well, I got 3g, 3 times 3 kilograms times little g, and then minus 2 kilograms times little g. That is the net force. I've added up the forces that are in the direction of acceleration. And I said that was downward. And so the net force is going to be downward. All right, so let's go see what's going on. What are my answers? What's happening to the center of mass? What is the direction of velocity of that dot? Well, it's downward, okay? So once you know that these are not correct, only focus on your 2 other options. Is the magnitude increasing or decreasing? Well, it started at 0 because it said it started at rest. Doesn't make sense that it would be started at rest and then go decreasing in magnitude, because that's not physically possible. That's why C is the answer. And I hope I explained it to you in a way that you can start to think about the center of mass and external forces of a 2 block system. We got to think of just more than the individual blocks. Number 16, 2 ice skaters, X and Y, are at rest on a horizontal surface made of ice. Friction is negligible. X has a smaller mass and pushes on Y such that Y travels with a speed 2v naught to the right. So here you go. The smaller one is here. The 2v naught is to the right, which meant that was a force Fx on Y. The force from X on Y. Okay, then I have this other mass, maybe this one. I have this other person who has a larger mass, and if I was putting a force, if X put a force on Y to the right, then Y is going to put a force on X to the left. That's Newton's third law. The center of mass is located pretty close to each other, right in the middle, maybe a little closer to Y, obviously, but there they are, and it's at rest. If the system is defined for us by the 2 skater system, so the 2 skater system, I can draw a picture around this whole thing and call that the system, and that dot represents the system that was defined for me as a 2 skater system. What's the velocity of the center of mass before the push? Well, the velocity initial was 0. Well, in order for the velocity to change, I have to have an acceleration. Definition of acceleration, change in velocity over change in time. There is no net force acting on this system. So even though the individual people move and their velocities change, the actual system velocity will stay the same because the net force on the system is equal to 0. Those forces from X on Y and Y on X, they're equal and opposite. They're internal and they happen to cancel each other out. It's a beautiful thing. So what is happening to skater X? Skater X is going to move to the left, but the center of mass is going to stay with a velocity of 0. So if you visually could see that skater X is going to move to the left, you can immediately get rid of C and D, and then you have to think about what is happening to the center of mass. Center of mass cannot accelerate unless an external force is acting on the center of mass of the system. Number 17. An object of mass m is dropped near the surface of Earth such that the gravitational field, what does that gravitational field phrase mean? Little g. That is what little g is. It's the magnitude of the gravitational field. On Earth, it's 9.8. It provides a constant downward force. What downward force are they talking about? Force of gravity. Which of the following happens to the center of mass of the object? They're going to define this system for you, Earth system. I have over here the object that's getting release of mass m, and I've circled the Earth. And where is the center of mass of the object and the Earth? It's located at the center of the Earth because the Earth is so substantially large with a humongous mass that that little teeny object above it is nothing. So that center of mass of that system is approximately located at the center of the Earth. There is no external force acting on this Earth's object system. Yes, there's a force of gravity acting on the object. Yes, that's also the same magnitude of force that it puts on the Earth, but that is internal to the system. So the net force that's external is equal to 0. The center of mass of that system, therefore, will not move. It started at 0, and it will stay there because of the fact that the external force is non-existent. Number 18, 3 blocks are sliding together to the right along a surface with no friction. When a force with magnitude F external is exerted to the left, so it's going to slow it down, on the rightmost block, as shown in the figure. The masses of the blocks are m, 3m, and 2m. If the force is exerted for some time, what is the change in velocity of the center of mass of the 3-block system? So I'm going to sum all the forces on the 3-block system. So here's the system's free body diagram. There's only one force acting on the system. It is to the left, and it is called FXT, right? That's only the force. There's no other friction acting on the system. The dot represents the free body diagram. I guess I can go up here, force normal, and this is force of gravity on the system, which is m, that's 6 m times little g, okay? This is 6ma. Let me put that down there. 6ma. All right. What am I trying to find? They want to know the change in velocity. Well, acceleration by definition is change in velocity over time. So if I create an equation for acceleration using Newton's second law, I can rearrange it for a and then use delta v over t. That's a table of friends memorization. Then I can solve for delta v. So summing the forces acting on the system, it's to the left, so I called it negative. And then I have the mass of the system, which is 6m times the acceleration, okay? They didn't ask for the magnitude, so I'm just gonna call that negative, and then you'll notice there are no negatives, so they could have called left positive for that matter. Okay, acceleration, therefore, if I rearrange that, is the negative F external divided by 6m. And by definition, acceleration is delta v over t. Now I rearrange, get rid of t, so that delta v equals something. And I will find that delta v, I left off my delta on the t, is equal to force external times time divided by 6m. And it's a. And hey, maybe they used to the left is positive. I like number 19 as well. Number 19, a block A of mass 4m is attached by a string, light string, in other words, don't worry about the mass of the string, to block B of mass 2m. The string passes over a pulley with negligible friction and negligible mass, that perfect pulley that doesn't exist. Block A is held some distance h above the ground as shown. The blocks are released from rest, and block A reaches the ground 2 seconds later. They want to know the value of h. It is a delta y. So I need 3 things, right? I know that velocity initial of that 4m block is 0. I know that I'm looking for delta y. I was told that time equals 2 seconds. I only have 2 variables. I need a. Okay. So in order to get A, I have to use the fact that I can calculate the acceleration of the system. The force, I'm just going to quickly use the system approach. The system is the 2 block string approach. The acceleration I'll assume is downward of the 4m, and that is positive. So what's trying to speed me up is 4mg. What's trying to slow me down? So I subtract 2mg. That's the force of gravity acting on the 2m block. What is the total mass of the system? That is 6m. The acceleration is a. I rearrange that equation for a. So 4mg minus 2mg is 2mg divided by 6m equals a. So I don't know why I'm okay. 2 over 6 is 1/3. 1/3 times little g. So 0.33 times, I'll say 9.8 equals 3.2. Feeling like I made a mistake here. 3.234 equals A. A now is equal to approximately 3.234. By the way, you can solve these with you assuming G is 10. 1/3 of 10 is 3.3. Okay. And watch, you'll get the same answer. I'll use 3.3. 3.3. Now I can go over here and solve for delta y. Delta y is equal to 1/2 times 3.3 times t squared. T squared is 2 squared, so 4. So that is equal to 2 times 3.3, which is equal to 6.6. You didn't even need to use a calculator if you assume little g is 10, and you can find the delta y there. And I will talk about that more in class. We cannot do that with expert TA, but for AP exams, you can assume G is 10. We're close. We only have a couple more. I got a situation where I have a 1 kilogram block. It's placed near the top of an inclined plane that is at an angle of 30 degrees with respect to the ground. In other words, angle of incline. The student correctly determines the effect of gravity, and they predict that the acceleration of the block will be 5 meters per second squared. However, they measure it experimentally, and they determine it's only 4 meters per second squared. What type of force did they most likely not account for when predicting the acceleration of the block? Look at all the answers. The answers have to do with force of friction or force normal. Force of normal is not in the direction of acceleration. It's most likely it's force of friction. It's either 0.1 newtons or 1 newton. So I went up here. I just proved that it was 4.9. I didn't have to do this part. I summed the forces in the x direction, which is down the plane, and that is Fg sine theta equals ma. That's 4.9. Again, I used 9.8. You could have used 10. You would have gotten exactly 5, I think. At any rate, now if I assume there's friction there, force of gravity down the plane, which is for Fg sine theta, minus the force of friction they forgot about, okay, I'll assume that's friction there, is equal to the mass, which is 1, by the way, we'll get there, times the acceleration they actually found, which was 4, so you actually were given it. You solve for the force, and you find the force to be 1 Newton, excuse me. I'm getting tired. So I solved for it. This is 100% not a force normal subject, okay? Number 21 is the last one. Magnitude of the force let me read the problem. We got a 3 kilogram object. It experiences a right horizontal acceleration of 6 meters per second squared as it slides to the right across a rough horizontal surface. Friction is there. Table above contains the label and magnitude of some forces. They're labeled 1, 2, 3, and 4. They could be to the right or to the left of the object, and it represents measurements from an experiment as the object accelerates. Which pair of opposing forces in which directions could be responsible for the acceleration of the object? Well, they told me it was accelerating to the right at 6 meters per second squared. That means I must have a force to the right and a force to the left because it's kinetic friction. And if I go over there and look at what this, oops, go ahead. I got some external force minus the force kinetic friction equals the mass of the object times acceleration. They told me the mass of the object was 3. They told me the acceleration was 6. The product of those two is 18. Here's what I know. These two forces have to add up to one, or the difference between those two forces must be 18. Okay, so I go and look at each one of these options. F1 to the right, F2 to the left. If I take those two and subtract 2 from 1, I get 24. C is wrong. If I subtract force 1 from force 4, I get a value of 0. That is accelerating at 0. And the same thing with D. I get a difference of 6. The only one that gives me a value of 18 is answer B. Hope that helps you further your knowledge and understanding of Unit 2.